Let's slowly get started. Welcome to our little two-day workshop. So this workshop is centered around two particular aspects of quantum error correction. So one question is the existence of self-correcting quantum memories. Essentially, that is asking whether we can have something like a hard disk or an SSD, where we just kind of put in a quantum state and can just kind of leave it, and the quantum information is preserved. And the other closely related question is the existence of local decoding schemes, so in particular serial intermittent decoders, which asks whether it's sufficient to have local information and then perform classical control on a quantum state in order to stabilize it. Okay, we have a great lineup of speakers on these types of questions. Obviously this is a workshop, so it's not all about the talks, but also about the audience kind of interacting with one another. So we have plenty of time for doing so. So we have the breakfast, we have tea time, we have coffee, we have lunch, and then we have tea time in the afternoon. So I hope you will kind of make use of that. The format is essentially we have two talks in the morning and then one talk in the afternoon, and we will make a start with David Lin, who will tell us all about proposals for 3D self-correcting quantum memories. Please take it away.
Yeah. Okay. Yeah. Thanks for the introduction. Yeah. Right. So I'm David, and today I'm going to tell you about the proposals for 3D self-correcting quantum memory. And this is based on joint work with Simple Wan and Ming-Shu Xie. And in between, we'll also tell you some more ongoing ideas. Okay, so we'll start by just telling you the statement. So the question that we ask is that does there exist a family of 3D local Hamiltonians? So these things are inside like a L by L by L blocks. And then under some kind of Glauber dynamic at low but constant temperature, a qubit can be reliably stored for an exponentially long time without active correction. Okay. So some of the things might not be that familiar to you, but I'll sort of build that up in the talk. Are there any quick questions? Okay, cool. So,
does it follow if you can store a qubit for exponential time that you can store large numbers of qubits?
Great. So yes, that's indeed a question. In fact, generally people know that probably one can store around L number of qubits, that's sort of an upper bound of L. I think that's also achievable, but for today's talk, we'll just focus on can we even store one, because that's already an open question. Any other questions?
What do you mean by Glauber dynamics, that this Hamiltonian will evolve in Glauber dynamics for this much time and still not disrupt?
Yes, that's the way to think about it. So in the case that we'll study, it will always be CSS code. So CSS code you can separate into the X and the Z, so it becomes like a classical kind of question. And so here, we'll comment on more later, but the Glauber dynamics here is really referring to the classical process. Okay, right, so we'll move on. Right, so this is a very long-standing open question. It has a very tight connection to physics because it's really about studying 3D Hamiltonians. And so people have been thinking for a while. And let me give you some other motivations, like why people might care about it.
So can you just remind me about Glauber dynamics? So what do you think is the rate of the, in the Glauber dynamics?
Yeah, we'll say more of that later. Yeah, for now we'll just do a very quick introduction. Yeah. So, so why do we care about this problem? Well, one is more of a technological argument. Currently people are trying to build these quantum computers, but these quantum computers really relies on some active error correction, and such process might sort of that just added some complexity. It would be nice if one can just run run a computer like a classical computer. In classical computer, just run it without very active corrections. So that's one of the idea. Let me just show a picture here. So here it's if you think about a classical computer, it might contain different components like communication and computation of memory. And for a quantum computer, in the long run, maybe you also have all these components. And so one of the things we might want to have is, again, some sort of object that's sort of like a hard drive in the quantum world. So that's sort of a technological reason. But there's also some physics in the audience, so there's actually also like a physics kind of reason why we might want to care about this. And in physics, what we want to do is really just trying to understand like what are all the possible landscape of like possible world that could exist, like what are the possible phases of matter, and so on and so on, like what are the possible universal behaviors. And so here's a sort of a cartoon picture of what's sort of going on. So on one hand, we know toric code very well. Like toric code, just a bunch of anyons which braids together. But you can do something more complicated. For example, you can go to other types of topological quantum field theories. So these are, again, sort of described by string operators, surface operators, but they sort of have a more like a weird commuting conditions. So in fact, in the next talk, we'll hear something that's sort of explored in this area. But there's another kind of generalization, which is you can try to put your toric code on some like a more complicated manifold or simplicial complex. And those are pretty much the underlying breakthroughs in these quantum LDPC codes. So we'll also hear more about that tomorrow in, I think, in Vedika's talk. So these, when you go up in this arrow, you go to like more and more complex behavior. But really at the end, like in physics, probably we really want to understand like quantum gravity or these high temperature superconductors, like these very complex phenomena. So you can think of like what we're trying to do is trying to just explore a little bit in this z direction. OK. And let me just continue using this arrow to explain the current situation about quantum memory. So what's known at this point is that 2D toric code, 3D toric code, they do not have memory. But in 4D, they begin to have these properties sort of because of some surface operators. Okay, I won't go into that detail. What I say is that a more general model is these topological quantum field theories. So as I say, they again have these kind of string and surface kind of geometric interpretations. And it's really because that in 3D, because of some dimension constraint, you always have some string. And these strings really just destroy the memory property. So it's very likely that if you just go to the TQFT world, there's no memory. So what if we try to go even further? Well, in 2D, you can study just generic gap phases. But it's quite believable that these gap phases, at least in the quantum case, they're quite related to these TQFTs. So it's generally believed that you cannot have memory properties. But OK, now what about 3D? Well, so for a long time, people thought that 3D gap phases are, again, similar to 2D, very closely related to TQFTs. But interestingly, in 2011, Ha found this model that actually is a gap phase, but is not a topological quantum field theory. So,
Can you maybe remind me like how the string logic operator kind of play into the next step correction?
So later on, we'll mention a property called this isoperimetric inequality. So what's going on is that if you have a string, inside the string, there is no memory energy cost. By the two endpoints, there's some sort of energy. But you can see that when you have a string, the energy is just constant. And so it often just proliferates.
It's like a 1D Ising model.
Yeah, like a 1D Ising model, so it just proliferates. But once you have loops, now your energy sort of just grows. And we'll actually say more about that later too. OK, yeah, but for now, I'll just say that string is generally a thing you want to avoid. And in Haas construction, indeed, it avoids the string operators. So that seems a good sign. But at the same time, there's also some fractal operators going on underneath it. And turns out if we really want to have a quantum memory, we also need to avoid some of these fractal patterns. And so, so for the rest of the talk, we'll really be talking about this regime. Like, can we have some sort of 3D gap phases that do not have string and also do not have these fractal patterns? OK, questions? OK, so what I'll do next is sort of, because the talk contains some like kind of a conjectural component, like things are a bit complicated. So let me just summarize my current understanding of the topic in like a chat context. So if you asked me before last week, like, do I believe 3D quantum memory exists? I would say, yes, very likely. So if you ask me how do I construct it, I would say a generic code probably already have such a property. So let me say a few words about generic. So So in fact, in many of these constructions, you can think of it as you're gluing a bunch of surface codes. Like you're gluing a bunch of surface codes along some sort of edges. And if you are familiar with this recent breakthrough about these BPT bounds, those constructions are about gluing L by L sizes surface codes. So here instead, what we do is to try to glue 1 by 1 size toric codes. And then we sort of glue them in some random fashion. Okay, I won't go into full detail, but the point is that it seems like by just gluing some generic 2D surface code, you would get these memory behaviors. At least that's my belief. But you can ask me, can I prove it? Well, of course, this model is so complicated that I don't think there's any chance of proving it. But just say, OK, all right, fine. Can you make this construction nicer, like to have more structure in your code? And the answer is yes. So we can have one version that's sort of translation invariant. And we can have another version that has a product structure. So it's coming from a hypergraph product code. And so these two versions are described in the paper I showed in the first slide. Yeah.
So maybe without going too much, how do you imagine that? Why would this give you like a 3D model? Like if you have randomly glue the edges of like surface codes?
I see. So the way to think about it is that you have a 3D region, and then you just have a bunch of small pieces of 2D size phases, and then they're glued.
But if you glue them randomly, completely randomly, then usually what you get is like something which is not necessarily embeddable in 3D, right?
Right. So here I mean it's kind of okay. So actually it's easier to give a classical code example. So in a classical, what do I mean by generic classical LDPC code with a geometric constraint? What I mean is sort of like you just put in a bunch of bits and you put in a bunch of checks and just connect them randomly.
Right. But the question is why is it embeddable in 3D?
Oh, so the way I pick those points is just picking a set of points in 3D, picking a set of checks in 3D, and just connect them locally.
I see. Okay.
And there's a sense that you can perform a similar operation in 3D. So some of people might heard of these topological defect network. That's sort of the thing I'm talking about. Okay. Yeah. All right. So okay. Yeah. Those are the two things that's known sort of before last week. But some of you don't know that 2 weeks ago there's the QIP, and after QIP I began to think more about this question for the talk. And interestingly, we have found a new construction, and this construction seems a bit more promising. It seems like there might be a chance that we can prove it. And so for the rest of the parts, we will try to talk about these three constructions. So the first construction, you can think of it as you take a 4D toric code and you just take a 3D slice. So now what you're left is sort of a 3D region. Okay. Right. Okay. So now I'll move on to the main parts. So before going further, let me just say a few words about this self-correcting codes, trying to give a more more concrete definition of what we mean by the self-correcting. So a key thing I want to distinguish is how these things are different from the traditional active correcting codes. So that's what we'll be explaining. So in self-correcting codes, what we do is, again, we choose a prior check matrix. But after choosing it, we will generate a Hamiltonian. So this code would be a sum of these stabilizers. What we'll do next is to couple this code with the bath. So we will keep the bath at low temperature, and then there is some interaction between the two. And so that's sort of the full Hamiltonian. Okay. So you might ask me, okay, I tell you what the Hamiltonian of the code is. What about the other two? And what I can say is just that, okay, these are complicated thermal processes. But the way to think of it is just okay, there's some generic thing going on. Because that's also why people often just talk about Glauber dynamics, because these things are kind of complicated to model. But we'll stick with this at this moment. So what we'll do next is try to illustrate how these errors are being removed. So on the left, we have the code Hamiltonian. So here I'm drawing the energy spectrums. So at the bottom, okay, so when you go up, the energy is higher. So on the bottom, that's a case when there's no error. That's sort of the code words. And when you go up, that's the case with errors. So that's for the Hamiltonian part, the code part. On the right, we have the bath. So a bath generally can be thought of as something that has a finer kind of spectrum pattern, and then we'll keep it as a low temperature T0. OK, so I'll try to give you some intuitions. And for physicists, you would clearly know that these are not correct, but I'm intentionally hiding some details. So let's consider a case. Suppose there's some cosmic ray hits our code. Then our state can probably move to a higher energy state. So it moves up. So what will happen next? Well, there is sort of a sense that you can argue that, OK, maybe this state has a higher temperature of some sort. Like now it has a higher energy. And now we can say, OK, well, this temperature is now greater than the bath. And so now the two sides want to equilibrate. So what that means is that, OK, in some sense, the energy wants to flow from the code to the bath. And if such a process actually happens, now your state on the code fall back to this no error state. And this energy is transferred to your bath. That's sort of the operating principle of these self-correcting memories. So you can see that in this process, I didn't do any really complicated measurements or anything. I just coupled to a bath and then just let things happen. And so in other words, what's saying is that just by cooling, in some sense, you can actually remove errors. But as I say, modeling these patterns, like thermodynamic process, is actually a very complicated thing to do. And so at first, we talk about this unitary evolution using some Hamiltonian. But instead, people sometimes talk about these like Lambolian dynamic, but it's still too complicated. So actually, in most of these work on self-correcting, people usually just model things using these Glauber dynamic, like some classical Monte Carlo process.
Yeah. So if the bath keeps getting hotter in the future, the errors won't be corrected, or is this too simplistic here?
OK. So what you're worrying is that, OK, like maybe there are some more and more error accumulates, then does that mean the temperature of the bath becomes higher and higher?
So you never go exceed it to release heat to cool down.
Yeah, that's indeed a possibility. But what's sort of going on is that you can think of this bath is coupled to some other bath, and so on and so on. And so as an example, like if you have a refrigerator, like you want to keep the inside of the refrigerator cool. So there is some process that kind of just sends heat from inside to the outside. So the outside is just the room. But the room is so large that it can just absorb heat, so on and so on, while maintaining the same temperature. That's sort of the idea. And so you can imagine that if we just, all right, this is just some crazy thing, but if you just try to put this on the moon or some other place far away from the sun, then it has a very, very low temperature, so you won't worry about these questions. Yeah.
Why do we expect the bath the other way around?
Oh, like why won't the heat goes back, right? OK, yeah, that's the part I'm hiding. So technically, the code, the state on the code won't just stay at the ground state. It will actually also just have a distribution that's sort of spread out. But one way to think about it is that you can think of this code over here has sort of a landscape. It's like there are some hills and some valley regions. And so if I design my code nicely, even if you're in a valley and if you just have some perturbation, you might go up a little bit, but you won't escape the valley to another valley. That's the picture to have in mind. And I think maybe in the later talks, someone would draw that picture. Right. So, right. So, right. I was trying to say that modeling these thermodynamic process, it's kind of complicated. So later on, we'll just talk about Glauber dynamics. And so indeed, there's sort of a gap, like a logical gap between these models. Like generally, it's not clear if showing quantum memory property at the Glauber dynamics implies that it will have some nice properties in the first two cases, but it's generally believed to be true, like at least in the physics case. So in this world, we just focus on the Glauber dynamic.
Are you trying to claim that 2 and 3 are different because of how you pick the jump operators?
So one thing is that in Glauber, yeah, that's right, the jump operators. So in Glauber dynamics, we really just think of x and z as completely separated phenomenon.
There are choices of jump operators in 2, which will just give you Glauber dynamics.
That's true. So what I want to say is that like in real life thermodynamic process, the jump operator is, you cannot choose a jump operator. It's like given by the nature in some way.
Sure.
And the claim is that it's quite believable that if you only prove the jump operator for x and z, that would also imply like our other versions are true. I think it's quite believable, but like it's just like I don't think there's a proof, written proof. Yes. Yep.
Do you think it's sufficient to look at properties of the just equilibrium Gibbs state, or is dynamics crucial?
So dynamics is actually quite crucial. So actually, in some of the talks later on, we will see that like there is some system that looks the same in some Gibbs state sense, but they have very different dynamical behaviors. So for example, the partition function is the same, but they have different dynamical features. Okay. So right. So now I will just remind people about this Glauber dynamics. Okay. So right. So if you actually have run some classical simulation, you sort of know what's going on. So what you have is that you have a set of different configurations, like different states. These states are labeled by some bit strings. And then your simulation would sort of contain some kind of process that transition between these states. And so, for example, later on we'll consider like these kind of jump operator that only involves doing a single bit flip. And so, for example, this A0 and A1, it could be like 0, 0, 0 here, and then like 0, 0, 1 over here. You're only changing one bit. And so what determines these transitions? It's determined by the energy of these states. So in our context, the energy is the number of checks that's being violated. So that's like the Hamming weight of HA1, HAI, and then beta is sort of the inverse temperature. And so these parameters would determine like how fast you transition between all these different states. So this really defines like a kind of a evolution process, like how these states just sort of spreads out into different configurations and so on.
So your weight is for each of these. So if they're L cubed spins, then it would be L cubed times this.
So A0 would be like, so N would be L cube.
Yeah.
Right.
So it's a per spin rate that you're speaking about.
Yes. That's right. Mm-hmm. Good. Okay. So that's the transition process, and using these kind of transition process, you can. Let me add one thing, which is that what's nice about this transition process is that it satisfies this detail balancing property. So here, if you consider the Boltzmann distribution, this transition rate would sort of make sure that the flow between any two configurations are sort of fixed. So in other words, the Gibbs distribution is really like a fixed point over this process, dynamical process. So once you have this process, you can now sort of formally sort of define what I mean by this memory time. So what I mean is that you try to first initialize your bit string at a certain place. This is like your code word. And then now you just try to run this kind of process for some time, like tmem. In the search process, like this distribution will be sort of spreads out. But we want to make sure that you can still sort of just distinguish between different kind of distributions. So remember the kind of valley picture I'm trying to say. So even though this thing sort of spreads a bit, but as long as they don't go through the valley, they can still sort of just figure out where things are. Okay, and there's some more formal way to describe these using random variables, but I'll probably skip this part. One thing I want to point out is that
the bit strings are just the eigenvalues of the stabilizers.
Great. Yes, that's right. Yeah. So currently, I'm describing a classical process, but as you say, like in a quantum case, especially CSS code, you can really split into X and Z. So it becomes like two classical processes, and the quantum memory is like the min between the two.
Okay. But maybe the question was like, if I had a non-CSS code, but still a stabilizer code,
yeah.
I imagine the same picture where like I'm thinking about like transitions between different eigenstates.
Yes. Yes. You can still consider that picture. I think in the theory world, people often just talk about CSS. The reason is that any stabilizer code can also be converted into a CSS code that Like if you have a stabilizer code that has memory property, then there also exists a CSS code with such property. So that's why we sort of just simplify things. But indeed, for practical purpose, you might want to optimize things. So that's also important to consider. Okay. So right. So with such a definition of TMEM, we can now formally define like what's the property we really want. So what we want is like we want to have a family of codes and a family of such decoder such that there exists a constant temperature, like a constant temperature beta, such that the memory time sort of just grows to infinity. Okay. No matter how slow is this, even just this property, like you want it to just grow to infinity, that's sort of open. Yeah, and the question is, like, yeah, we want the 3D version of this.
Where did the decoder come in? Is the decoder
Good.
like the bar?
The decoder is this. Yes, the decoder is, so I mentioned that this sort of distribution sort of spreads. At the last point, when you want to retrieve the information, you will sort of want to just pull it back down. That's the decoder I'm talking about. Okay. So yeah, so in fact, the definition often encode the decoder component, but indeed, like most of the time, people just hide that part. Okay. Yeah, and right. As a side comment, people generally actually want this time to grow very fast, like exponentially. And the nice thing is that if you can grow it exponentially fast, then you can actually make your memory very small. So generally, people want this exponential growth behavior, and we'll actually see that. At least we think it's possible. It's indeed possible. Okay, that's sort of an introduction. Oh, actually, yeah, there is a. We'll actually see a simulation here. So those processes are kind of abstract, but we can actually really just run this in like 1D Ising model and 2D Ising model. So here consider a case where you have a bunch of spins on the line, and then your Hamiltonian prefer them to be pointing in the same directions. You can sort of run this Glover dynamics, and we can see is sort of this kind of behavior. So what I want to point out is that in the beginning, everything is sort of pointing up. That's where where you initialize your state. But after just a short while, you can see that everything just becomes pointing down mostly. And so what I want to point out is that in the 1D Ising case, indeed, you cannot. Your memory time is really just constant. But instead, if you do the same thing for the 2D Ising model, you'll see is that it often just stays the same. And actually, you can show that the memory time is indeed exponentially growing as the system size. So why do we have such a behavior? So here, let me give you another simulation. So what I do here is that I first initialize everything pointing up. So that's like the yellow part. But in between, there's a sort of block that's pointing down. And we can see how it evolves. So you can see that the boundaries sort of just move side by side without a preferred direction. But if you try to do the same thing in 2D Ising, you'll see that it just gradually contract. So that's also a defining feature for these memories, which is in physics is also known as some kind of confinement features. And these confinements are, again, very related to these isoperimetric inequality. So let me say more on that. So if in 1D, if you just pick a region, then the boundary of it is at most a constant times just at most a constant. But in 2D, if you pick a region, then the boundary is at least a square root times some sort of constant. So at least a square root. And this property where the power is non-zero is actually very important. And it seems generally true that if you have such a property, then that often leads to confinement phenomenon, and that actually also leads to this quantum memory. So this is just a code for the simple Ising model case. But you can actually translate all these languages into the classical code and quantum codes. So here, the property that you want is that your energy. So remember, H is the parity check. So HV is like the number of syndrome that's violated. So that's your energy. What you want is your energy to be greater than a polynomial of your error. Okay. And you can pretty much extend the same thing to the quantum case. So I won't go into the full detail, but quantum, you have two parity check. So on the left, you again have an error term, the energy term, And on the right, you have sort of an error term, except that now you also only define this up to the stabilizers. So that's the property we sort of want. But in fact, we can also weaken it a little bit. So all we need is just a small set kind of condition on these. So what we need is actually just to show that for every vector with a small weight, this kind of expansion sort of holds. And in the quantum case, it's often also sometimes known as these kind of small set co-boundary type of conditions. So we'll actually see more on that in, I think, in Vedeka's talk. Okay. So let me make a few comments on this. So the first thing is that as I say, this condition is actually very close to self-correcting codes. Like all the difficulty is really just trying to prove this inequality, and we somehow cannot prove it. The rest of the remaining part is sort of like a standard Pyrrhus argument. So this is really the sort of the key. And in fact, for certain conditions, these epsilons are sort of bounded. So for generic LDPC codes, it's known that this epsilon has to be less than 1. And for expander codes, exactly 1. So that's why we know that these good quantity PC code have nice kind of memory features. But here we're talking about the geometric one. So you actually have even stronger constraints. So for d-dimensional local codes, for classical codes, epsilon is less than d minus 1 divided by d. And for quantum, it's d minus 2 divided by d minus 1. So these are sort of similar to those like BPT bound. Like you can sort of see these from there. And so what it means is that if we just focus on these stabilizer code regime, there is a very strong constraint on the dimension. For classical code, the dimension really had to be greater than 1. And for quantum, it really had to be greater than 2. Mm-hmm. Okay. Yeah?
Why is it called an isoperimetric inequality?
It's like parameter. Like there's this, in classical world, there's this question like, OK, in 2D, if you draw a region that has area, like area 1, what's the smallest boundary? And then the answer is a circle, and that gives you the inequality, sort of. Yeah, this inequality.
It's just like a minimum energy barrier scaling. Oh.
Yeah, if you translate into that language, that's right. That's right.
And those bounds?
Maybe stronger than energy barrier. So these bounds are stronger than energy barrier. I can say more of that offline now.
Okay. And those bounds that you wrote with d greater than 1 and d greater than 2, you're probably going to want to get around those bounds, right? So they're...
So what I'm saying here is that
okay.
these are required.
Okay.
So for example, in classical codes, it's sort of known that if you put Ising model on like 1 plus epsilon fractal, it has memory. So that's the kind of thing I'm saying. So in quantum, I think it's believable that you can do actually in 2 plus epsilon.
But maybe just only 2D is ruled out, right? Like it's like the Ravi.
Oh yes. So here I'm saying sort of the kind of same kind of thing, except that in this type of language. Okay. All right. So good. Yeah. So just to summarize everything. So what I want to say is that there are a lot of things that's unknown in this self-correcting world, but it oftentimes boils down to this issue like we cannot show isoperimetric inequality. That's really the key.
So David, so here you're correcting some fraction of errors, like only n to the mu errors, not a constant fraction of errors.
Yeah, we don't need to worry about that because those things only appear in like very long time scale. Like, okay, I think it is true that okay, all right, I'll be wrong about what I'm going to say, but like these parameters about mu, it will tell you about how long your memory time scales. So in some slides, I say the memory time is sort of exponential to the power is like poly n. These mu would sort of tell you something about those. Okay. So I think that's some abstract thing I'm going to say. These are all the sort of more kind of framework kind of aspect of things. Like later on, I'm just going to talk about constructions. So before moving on, is there any questions? Okay. So now we'll just talk about constructions. And great. So the first construction that I'll talk about is this translation-invariant one. So for people that's following this field, you know that this, like I mentioned this Haas construction, like the Haas code. So really, this construction can be thought of as like a generalization of these kind of Haas construction. So let me give you some background on that. So in Haas construction, he sort of used this language of like polynomial method. And so for people in like classical coding theory, you know about cyclic code. So these are really like cyclic codes, except that now you have 3 dimensions. And so let me go into more details. So here, the first thing we do, what you should have in mind is, what you think about is that, okay, now we have a lattice structure, like an integer lattice, and at each integer lattice point there is a qubit. And I want to describe a code on it. So first thing we do is that for each lattice point, we'll associate with a monomial. So here's an example in 2D. So at the center, this point 0, 0 is associated to just 1. And if you move to the right, you get x. Move to the left, you get x inverse, and also y and y inverse. So now what's a parity check? A parity check is just a set, like where the qubits acts on. So for example, here, if a check acts on these 4 qubits, then what we can do is to associate with a polynomial, where I just like add up these monomials. So what's nice about this is that if our code is translation invariant, so like that means if I have a check somewhere, if I move it one step in the x direction, it's also a check. So that means if f is a check, x times f would also be a check. I just moved the thing one step. And more generally, if I multiply by a monomial, it's also a check. And so overall, what's going on is that to specify a translation invariant code, all I need to do is just to find some of these functions. And often it's just a finite number of like polynomials. So previously, since the system is like very large, you might thought that I have to specify many things. But actually, all I need to do here is just to specify a finite amount of data. OK. But more generally, at each lattice point, you can actually put more than 1 qubit. You can put multiple qubits. So in fact, a parity check does not just correspond to one polynomial, but actually a vector of polynomials. So let me explain that. So imagine that you have your lattice, and at each point you have like first qubit, second qubit, third qubit, first qubit, second qubit, third qubit. And now the first polynomial, the first one, the first polynomial will tell you like where you act on the first kind of type of qubits. So as I said, f specifies like a set, and that tells you like for this check like where you act on the first qubit. And f2 will tell you like where you act on for the second type of qubits, and so on and so on. So now this whole vector sort of specifies which qubits this check acts on. But again, there might be multiple checks instead of just one. And so really, at the end, what you have is like a parity check matrix. But now your entries are labeled by these polynomials. OK, and so let me actually give you an example of that. So here, it's just the standard toric code. So these dots are the qubits, and the blue are the x check, and the red are the z checks. OK, and then this blue check act on these 4 qubits. And what we'll try to do is try to read out these polynomials from here. All right, so first of all, let's look at this x check. So it acts on these 4 qubits. And for the first type of qubits, so the one on the bottom right, you can see that it acts on these 2. Okay? And so they're sort of in this first block, and also this block at x inverse. So that's why this first entry is 1 plus x inverse. For the second type of qubits, so it acts on like here and here. So they're within the first block, and then this like y inverse block. So that's why it's like 1 plus y inverse. OK, and you can try to do the same thing for this other z, and then you can, again, read out some polynomial. All right, so next thing you would do is to say, OK, well, in CSS code, we know that they have to satisfy some sort of commuting constraints. So what's going on here for these polynomial stuff? I won't go into detail, but I'll just say that, again, it's just a multiplication of 2 multiplication of 2 matrices, and you want them to be 0. And so just to summarize, for these translation-invariant code family, you can really specify them by just finite amount of data. So you can specify them by two matrices over these like Laurent polynomials, which satisfy this property that they multiply to 0. And so now we just want to find some code inside this family. And the difficulty of finding these codes is often just to satisfy this constraint. Like satisfying this constraint is often a tricky part. And so one way you can do that is perhaps, like for the purpose of constructing code, you might just say, OK, let me just find all possible matrices that satisfy such property. Like you can do a numerical search, and for example. But this is generally quite time-consuming. So instead, an easier way is to often just find a family of solutions. So for example, here, f and g are just arbitrary polynomials. But as long as hx look like this and hc look like this, they always multiply into 0. So now what that means is that you can just insert arbitrary f and g, and that would define a code. And that's exactly the Haas code. So if you put f to be 1 plus x plus y plus z, and g to be 1 plus xy plus yz plus zx, then that would define your code, define the Haas code. So, and as I say, it doesn't have these logical, like string logical operators, which is already quite interesting. But at the same time, they have these fractal patterns. So that's why they're probably not memory. So we have to go beyond this type of model. So what can we do?
Sorry, when you say these fractal patterns are lacking on self-correcting, it's because they don't fulfill this like
Good. Yes, great. Yeah, great question. Yeah. So when I say these fractal patterns, they likely don't have self-correcting. One indication is that they do not satisfy the isoperimetric inequality. But on the other hand, people have also done these simulations. So it does seem like they do not have these self-correcting behaviors. So we have to go beyond this type of models. And so in other words, maybe you want to find another family of solutions.
You can show that none of those, if you have these fractal operators, they don't satisfy the isoperimetric inequality even for only the small weight. You had this condition where you only required it for it was less than.
Right. So one, the example I have in mind is that so when you have these gaskets, right, let me just draw.
Yeah, I guess for the gasket, it kind of makes sense, but that's a general statement.
Oh, the general. Okay. So if you look at Haas' thesis, there is a part that he defines some sort of fractal generators and so on, and there's a sense that for this kind of model, like fg, g minus f, they always have fractal patterns. So in our paper, we also actually reproduce some of those arguments. Yeah, I can comment on that more later. For now, what I want to say is that having just this solution always have fractals, and this family won't work. So we need to find another family that satisfies this multiplication equal to 0, this kind of constraint. So one way to so we want to understand what's going on. So one way to understand it is to rearrange this picture into this kind of commuting diagram picture. So here you can see that if you go from x to z, you can do fg and then g minus f. And this kind of property is very related to this equal to 0. So what I want to say is that this fact that fg minus gf equal to 0 can be represented by this square over here. And so once you have this idea in mind, now the question is, OK, how can you have more squares? And the answer is just do square complex. And in fact, in Kona LDPC codes, that's really the trick to sort of go beyond just toric codes. For example, these hypergraph product codes. So let me just say that, yes, so using this kind of idea, you can find another family of solutions. And so the belief is that just by filling these f and g with these random polynomials, or with a suitable choice of polynomials, perhaps they would have these memory properties. OK, so I won't have time to go into the detail of how we got those matrices, but let me just flash through a few ideas. So what we do is to take two bipartite graph, and we can take a Cartesian to form some square complex. Then we can assign functions for each of these edges and sort of transfer those functions into this square complex picture, and they would naturally satisfy these commuting constraints. So that's sort of how we can generate those matrices. And for this construction, we'll call it the m=2 model in the sense that the graph that we use are like these bipartite graph has 2 vertices on the left and 2 vertices on the right. And in fact, for the Haas version, you can think of it as an m=1 construction because it's just one square. And yeah, so this is the conjecture I was mentioning. So the belief is that if you find some suitable choice of polynomial, you will actually get all the best parameter one can hope for in geometry local codes. So the first line, these saturates the BPT bounds, and but today the focus is on this memory time. It's quite different. So let me just make a quick comment. So in layer codes, you have these very large patch of L by L toric code, and so what I want to say is that essentially it sort of behaves like a toric code. So actually it does. Right, it's not proven in full detail, but it's very likely that they do not have memory properties. Whereas for these things, the branching structure sort of just happen at constant size. So yeah, right, let me try again. So for layer code, the branching structure sort of happens at the scale of L. Like you can move a line L, but then you have to branch and branch. So that's what gives the large energy barrier. But here, the branching already happens at constant scale, so it branches very fast.
So those layer codes, because you have to go that large, you have a large energy barrier, but you also have a lot of entropy. So that's probably why that isn't, because you can move in these directions a long distance very freely.
Yes.
So that's probably why you don't have a memory in that. But if you can do this at constant scale, then that's what you have to remember.
Yes. So layer code have those features, whereas this one, they don't.
Did you say what the logicals were for these codes?
I don't. They're probably complicated, but I'll show a picture later.
But you had said, for example, like in the FG, minus GF.
Yes.
One's always had fractal.
Yes. Okay, I'll show a picture. very soon. The 2 slides later.
Can you get these parameters, at least for the rate and distance?
So forget about memory. That's achieved very recently. So the construction utilized good quantity PC codes. Okay, that's a layer code construction that we were talking about. Yes. So if we just care about parameter, it's possible. Like people know how to do it now.
Is it with this framework of these?
It's a totally different construction.
But I guess my question was, with this framework, do you know how to get the parameters without the memory?
I see. I don't think I know. Yeah, I don't think I know. Yeah. In fact, I think for the Haas code, I think that bound is also not so easy to get. I could be wrong.
I think the Haas code was really complicated. You need like some kind of GCD of like the two-side length and so on. It was really hard to analyze. I don't know, but I don't know whether it was resolved.
Yeah. Things like that. Yeah.
And in Haas code, you won't expect D to be L squared, right? Like it would be more.
Yeah. Also, that's right. So generally, if you look at this G minus F, that kind of regime, the distance cannot be 2. It's at most 2 minus epsilon. Okay. So right, all I want to comment is that like all parameters, if we can do this, then all parameters are optimal, and it's quite believable that like these things are again very generic. Like just pick any random polynomials, they probably have such a property. Just like random codes are good, like sort of that kind of belief. Okay. But all right, let me check the time. Great. So, okay, but if this is the first time you think about this, you might say, okay, well, in some sense, this construction is not that different from the m=1. You just find some family and just fit in some numbers. Like, what's the difference? Like, why there is such a sharp distinction? And as I sort of mentioned, the distinction is really because of this fractal generators. Like, on one hand, there's fractal. On the other hand, it seems like there's no fractal. And let me just show you a picture of how it looks like. That's how the logical operator looks like in this family. So, yeah, at least as far as I can tell, I cannot see any pattern here. So what I say is that it's very generic.
What was the choice of
Oh, ooh, I didn't write it down, but I can.
What about the degree?
Okay, good. So I can say that the way I generate this is sort of through some MDS codes, because maybe like I forgot the full name for MDS, but these codes has generally like they saturate these singleton bounds, so they're in some sense very good, and so these codes are sort of induced from there. Maybe the weight is 8 or 16. Let me just send something like that.
If you choose a random m=1 code, does it obviously have fractal structure?
Yes, one can often see that. Oh, okay, let me put it this way. So one can explicitly construct a fractal pattern that has like an explicit fractal logical operator. But at the same time, if you just randomly sort of sample it, like you just run a Glauber dynamics, you can, again, often see like these pieces of fractals appearing. Okay, right, so the logical operator is very complicated. On the other hand, we also do some other simulation, which is related to this thing of like shrinking. And we can indeed see such a phenomenon. Like the dark part are just like initialized to like 0 in some sense, and then we can sort of see the region sort of just shrinks. So that's sort of an indication, but I would say it's a very weak indication. Like you shouldn't take this as a reason why you should believe like these objects exist. What we really want to do is to really do some sort of finite size scaling. So what I mean is that you want to sort of create these memories at different scale, and then like really just try to measure the time when this memory just breaks. So you get the memory time and then try to fit a curve over it. And in Haas's code, I think you can see that this scaling is polynomial, whereas in these models, I think the belief is that it should be exponential. So it would be good if we can see a sharp distinction there. But turns out we can only simulate these things for a very small size because, well, we believe that they're exponentially growing, so that's saying that it's hard to simulate. And that's sort of a dilemma. Like, we think that they're complicated, but we cannot prove they're complicated because they're complicated.
This is you run into a time barrier, not a system size barrier.
Yeah, like the time. Okay, yeah, so we cannot really carefully distinguish these two. But let me just, at the end, let me just give you another like more of an analogy kind of argument here. So if we take analogy to like cellular automata, then we sort of know that if you run very simple cellular automata, you will get these periodic patterns. That's sort of like a toric code. But if you run something more complicated, you will get some fractal patterns, which is sort of like this kind of like Haas construction. But we also know that in cellular automata, if you run something even more complicated, you'll run to another regime, like these Turing complete regime. And so what we're suggesting is that maybe there is also a similar regime for these linear codes. So these would definitely not be Turing complete. Okay, they're probably not Turing complete in some sense because Turing completeness requires some nonlinearity. But all we want to say is that maybe this provides you a new regime. Okay, that's all I want to talk about on this translation-invariant part. Any questions?
So the simulations you were talking about were explicitly initializing some region which is a big droplet, and you're trying to get rid of it.
For this one, this is what I'm doing. But what we really want to do is we initialize everything to be the code word, like the ground state, like in the 0 ground state, and then just try to evolve things over time, and then at time t we ask, can we decode it so that it looks like let me try again. So I can say what Ha did. So what Ha did was that he take the logical 0 state, do some evolution, and then he wrote down a decoder that tries to decode the resulting state. So sometimes it will succeed, sometimes it will fail. And he just looked at where things begin to fail very dramatically, something like that. So that would tells you like the memory time.
Does the gap of the Markov chain tell you anything?
Okay, I'm just thinking about it more, but we can talk about it more later.
So do you know that your code has, these random codes have the parameters that you said with D and K?
Yeah. So I don't.
You don't. Okay. And do you know what the energy barriers?
Oh, yeah. I just know nothing. Just construction. Period. Yeah. I have nothing more to say. in fact, these versions has some classical counterparts, so I can also talk more about some like open question, even in the classical code case after this. Okay. So what I want to do is sort of skip the second construction and just move on to the third construction. Okay. But I'll just say a few words here. So the second construction is based on these kind of fractal product. So the main thing that we one of the motivation was in like the Sparrow's code. So he was considering these construction that's based on taking like a hypergraph product of two of these like Sharpinsky carpet patterns, and the hope, like he was hoping that okay, maybe it's self-correcting, and well, there's another question about some embedding questions. Turns out the second question is doable using some of the more recent breakthroughs on these embedding, sort of geometric kind of embedding questions. But unfortunately, this code is not self-correcting. I won't go into the exact reasons, but again, it's some isoperimetric issue. But nevertheless, one can try to just make this classical code more complicated, like the one he used more complicated, and the belief is that there's some variance that could be a quantum memory. The nice thing here is that it has a product structure, so you can imagine generalizing into higher dimensions. Like I can take 3 or more 1 plus epsilon fractals and tensoring them, which actually could have some computation abilities. So, but that's for another day. At the end, I just want to now come to this third construction about this, like sort of a slice of a 40 toric code, or a boundary of a 40 toric code. Okay, so this construction is actually motivated by a visit I did in November to Harvard. So over there, I was giving this first construction and second construction. But interestingly, over there, there's also a group thinking about these questions, but from a totally different perspective. And that's actually what motivated this. So let me say a few words on that. So their construction, I should say that it's not on archive yet, but I think it will be there maybe 1 or 2 weeks. So the construction is based on like this kind of quasi-crystal idea. So in the framework I just sort of described, like I always say that okay, doing something random, it will be great, but but random is also hard to analyze. So their idea is that okay, what if we just do some aperiodic tiling? Like it seems random, maybe it's good enough. So here, for example, here it's like a Penrose tiling. And one way to think about these Penrose tiling is that you can think of it as a slice of a higher dimensional structure. So in particular, this thing can actually be thought of as like a 2D slice of a 5D kind of lattice. Well, it's impossible to draw this, but let me do a similar version. So here I'm taking a 2D slice of a 3D cube. So you look at this picture, you can sort of look at it in a 3D way. Like it seems like there's a cube, and then it's filled by some small cubes. Okay, can people see this? Okay, great. So that means you fill in some cubes, and then now you just look at it diagonally. And there's a sense that you can think of it as taking a slice, like a 2D slice of this 3D structure. And what I want to say is that, yeah, this is the same thing here. Like if you imagine some 5D structure, and then there's a sense that you can take a slice, and that's the pattern you will get. And so this leads us to think, okay, so why not just take a 3D slice of a 40 toric code? And so that's what we'll explain. But let me just do the simple one. Like let's just first talk about the 1D slice of a 2D torus. All right, so here, this is the usual toric code. You have the checks on the vertices and the faces, and then you have the qubits on the edge. And they extend in all directions. So now let's just take a small slice. So now it still extend up and down, like, but left and right, it's like just constant width. So now one can sort of view this as this kind of cartoon picture. So can people see like the gray, like the background here? It's pretty faint. Okay.
See it on the screen.
All right, yeah. Okay, so you might want to look at some of the screens on the side. So in the bulk, you have, in this cartoon picture, in the bulk, it's like a 2D toric code, and then Oh, sorry. Let me try again. So what I want to say is that on the left is a lattice picture, but you can often draw a cartoon picture, which I'll draw in this way. So in the bulk, it's some gray area of this 2D toric code, and on the two sides you have this smooth and rough boundary, which will be colored into like blue and red. Okay, and again, the thickness will always be as a constant. So once I draw this picture, now you can begin to imagine what you can draw more. For example, this kind of thing with alternating boundary. Okay, and so that's really the idea. So now so taking a slice of a toric code can now be thought of as just trying to apply coloring the boundary of like a 2D toric code. And so that's the perspective we'll take. So now in 4D, what we'll do is to take the 4D toric code, and then now there are two 3D boundaries, and what we'll do is to just color them. Like the remaining question is to find a way to color them. And for concreteness, we'll think of these 3D boundaries as like S3, like 3 spheres. Oh, not that important, not that important. You can also think of it as R3, yeah. It's just that at the end, we want it to be finite size, so I'll just use S3. And the point is that because this thickness is constant, the whole thing is really 1D. You can really embed the whole thing in, embed the whole thing in 3D. Okay, so the rest of the question is to color the boundary. So what can we do here? So first, let's just try to color the boundary on one side. So first, let's forget about the right side. So on the left, let's color here in this alternating pattern. And this pattern, you will see like two logical operators. Okay, and you can see that they anti-commute because they intersect at one point. And what that means is that they actually define a qubit because you have an x logical, a z logical, and they anti-commute. We can now do the same thing for this 4D case. So it's known that S3 can be cut into two donuts. So imagine you have a donut. So what you do is you color the inside, like the inside of the donut in blue, and you color everything else in red. So that's this picture. In this picture, you can find the logical operator. So the logical operator is formed by, first taking, so again, these logical operators are like two-dimensional surfaces. So where's the two-dimensional surfaces? You first draw a non-contractible loop inside the donut, and then you can sort of fill in the surface in this 4D region. Okay. That's for the blue loop. You can do, again, the same for the red loop. So now the red loop now goes in in the other direction, sort of, and then you can, again, fill in the surface in the 4D toric region. And amazingly, they also have exactly one intersection, and so they form a qubit pair, like a qubit. So that means the remaining question is to color the other side. All right, so what can we do? So what should we do here? Well, it turns out the other side is a bit tricky. Like, if you don't color it carefully, they can destroy the memory. So let me give an example. So here is one of the logical operators we were talking about. But now, because the thickness is 1, the anion can actually tunnel from the left to the right with just small energy cost. But this string sort of intersect with the logical operator, so actually it would change the phase of the information stored, so it's no longer a quantum memory. It can be at most a classical memory. Okay. And it turns out the same thing can sort of also happen in the 3D case. I'll just simply say that you can create like a logical operator that sort of extend. It's like a cylinder that extend on the two sides, and this logical operator can be created with just constant energy. So there's no energy barrier even, and that means this red logical operator cannot store any quantum information there. Okay. So what I want to say is that we really have to design the other side very carefully, and like how can we do that?
So I didn't quite catch why is quantum energy? Like what's
good.
The shape of this thing?
Yeah, I'm trying to skip that, but let me say one word. So it's like a cylinder, and so what's happening with the cylinder? This circle part is large, the scale here is proportional to L. So that has a large circle, but the cylinder has a very thin width. the width is really just this width of the Fourier torque. So it's just constant width. And so now you have a cylinder with a large circle but the constant width. Like, how do I create it with low energy? One way to do that is to form sort of like a what is it called? Like a band, sort of, and then now I can like sort of bring it over. And the only energy that is cost is somewhere near this part of the band. Yeah, so it's a constant energy process. All right, but okay. The key is that how do you design the other part, other side of the boundary? And so one thing to note is that if you color in the opposite color, it's sort of a good idea, because now you can see that it cannot just tunnel through. But it's not enough, because you can still tunnel near this kind of sort of interface interface. So all right, so now if we come back to this question, how can we color it? Well, what we can do is to say, OK, we don't know how to color the full thing, but at least we know that there should be, like, generally we should color using the opposite color. So let me explain what is going on here. All right, so you have a donut on the left. You have a donut. And the interface between the blue and the red is like a torus, just on the surface of the donut. So away from the surface, you would color with the opposite color. So the remaining part that's not colored is really just near this torus region. Okay. So in this picture, what I mean is that so if we look at the interior of this donut, then away from the boundary would be like a shrinked kind of donut. That's sort of what this red part is about. So you can see that this red is like kind of like inside this blue region. Yes. Okay. Yeah. Right. So you have yeah. Okay. So more mathematically, you can. What I mean is that you can split this S3 into the red part, the red donut, the blue donut, and then like the interface regime where we haven't colored it yet. And this interface regime is like a thickened torus. So what I want to say is the remaining question would be, we want to color this remaining piece. So yeah, so that's the torus picture, and then we can again just sort of open it up into this type of picture. So it's really like S1 times S1 and times the D1, and all of them would has like the size proportional to L, like they're not constant, they're sort of extensive. I want to color it. So the simple thing to do is, OK, all right, coloring the whole thing is a bit too complicated. Why not just color the torus and then just extend the answer? So that's what we'll do. So the remaining question is just to color S1 times S1. All right, so how do we color it? So we have to know what's the property we want. So one of the property we want is that we want the coloring to have no blue vertical line and no red horizontal line. There is something related to like these patterns would destroy the memory on the left side. OK, but let's just think about this problem. And if you just go back and try some coloring, you'll see that, oh, there's always some blue vertical line or some red horizontal line. You can try more options, but you'll always see that it does not work. Like, no matter how you color it, two colors do not work. So what do we do? Well, you choose more, you create more colors. So how do you create more colors? The way to create more colors is by having more copies of toric code. Because these colors is really about like what are the gap boundary conditions. So once you have more toric code, you have more kind of gap boundary conditions, and that leads to more colors. OK, and let me just say a few more concrete things. So now we have, say we have n copies of toric code. Then the color would be like a subvector, like a vector subspace of f2 to the n. OK, and if you're a physicist, the way to understand this is that, OK, like each color is related to like a gap boundary. And if you're a computer scientist, if you know about these works on LDPC codes, these colors are really like a local code. It's like a choice of a local code. OK, and just to say something even more explicit, so if your C is spanned by 111 and C perp is spanned by 110, 011, then it's same as condensing this E1, E2, E3 particle and then M1, M2, M2, M3. So there is really a direct relation there between color and gap boundaries. OK, so now we have a bunch of colors. So what do we do? So we now cut this torus into like small hexagons. So these small hexagons has like constant size. So there will be roughly like L by L many hexagons. And now we just sort of color them somewhat randomly. So you can see the color on the side, yeah. So we just somewhat color them somewhat randomly. But actually we don't just color completely randomly. Like we want to make the color sort of have a very smooth gradient. So what I mean is that the nearby hexagons should have the similar color in the sense that their vector subspace, they have a large intersection. Like the intersecting space is like almost like they're only off by like one vector, sort of. Okay, so so it seems like with this a lot of restrictions now we're able to like sort of analyze this model, and that's we'll try to like finish all the argument, and so the rest will be to be continued. And so let me just conclude. Yeah, so at first we describe these Gauver dynamics and then talk about these isoperimetric inequality. So this isoperimetric inequality is really like the key to show a bunch of these self-correcting results. And then we sort of describe 3 of these constructions, and the last one seems like the most promising one that we can try to prove. Okay, so what are some future things that might happen? So of course we'll try to complete this argument, and hopefully we'll succeed. But another question that sort of came out in these earlier work is that, so it seems like we have a lot of constructions, but there's just no way to test it because the memory time just grows exponentially. And well, what I mean is that the only diagnostic we have is the memory time one, which grows exponentially, and that's not a very efficient way to sort of test these properties. So one might wonder, are there other ways to test it? But at the end, I would just leave something like more open about these physics implications. So in fact, like what we're trying to do is you can think of it as sort of trying to explore something beyond fractal. Okay, so what is a fractal model? It's like something that's beyond TQFT. But the fractal we understand are like the most complex one is sort of like so we have the x cubed one, but also like the Haas one, like type 1, type 2. But what we're trying to say is that, okay, there seems like there's even a newer regime, and maybe it's worth understanding like what's going on, et cetera, et cetera. On the other hand, the last model I mentioned that there is something that varies sort of smoothly. And so it turns out this model can also be, it seems like one can create a similar field theory model on it. And so it's kind of interesting, like we might also try to understand what this field theory model is trying to do. And yeah, hopefully these works would lead to better understanding of like the general kind of complex behaviors in physics. Yeah. Okay, that's everything. Yeah, thank you.
Thanks, David, for the nice talk. Maybe let's have like a couple of questions, and then yeah. Go ahead.
So I have a question about like the last point you made. So at the beginning, you explained some intuition about how like a TQFT in 3D should not have any kind of like self-correction property. But it seems like the last thing that you did was constructed as some like kind of defect network in 3D. So like why does this evade that intuition?
What I want to say is that a defect network, the behavior defect, really the key here is indeed about like defect network features. So there's actually a generic fact, I think, which is that any 3D like CSS code, let me try again. Like any CSS code that's geometry local in 3D can always be phrased as a defect network language. So like gluing things on the boundary. So what I want to say is that that's a very generic language, and there's sort of a sense that so TQFT, it's not exploring the possibility of putting complex geometries, whereas here, like I think all the the power that we gain is really by just studying very complex geometries. And so I'll actually say the same thing for these good quantity PC code, like these breakthroughs, because there's a sense that they're really just putting toric codes, 2D toric codes on some 2D simplicial complex. And again, all the breakthroughs come from the fact that now we can construct very complex simplicial complex.
Yeah, for the first part, instead of like computing the memory time, have you tried just like randomly sampling low weight strings and seeing if the isoperimetric inequality is satisfied?
Yeah, they're satisfied, but usually I consider that a much weaker evidence because the memory. You said
it was like if and only. Well, you were regarding it as an if and only if.
Yeah. So I would say this is if and only if, but this is like a worst case behavior. whereas randomly sampling only gives you average behavior. So it's possible that there is a code that on average it has isoperimetric. But whenever you have something, like even if you have one thing that's bad, that could just proliferate and just destroy the whole thing. So that's a discount.
The average case for like, why is the average case not important? Because very small entropy if you have only one sort of.
Maybe we wanted to say is that like the bad behavior could be like the case where the bad behavior happened could be small, but like because it might still be large enough that they dominate in some like even after energy suppression, those things. But indeed, it's a test. It's a test, but it would be great if it's even more concrete, like something that's even closer to.
But does that test work? Did you try it?
One can argue that one can argue that this test is very related to that type of test, and because here I'm actually even sampling it more thermodynamically, so it might even be a better test, arguably. I don't know.
Okay, maybe let's move the other questions offline. Let's thank David again for the very nice talk.
Thank you.
And we have a quick coffee break now. Maybe let's reconvene at 11:45.
Thank you.